Hi guys! This is the second part of the two-part lecture on the topic triple integrals in spherical coordinates. In the last video, we learned what spherical coordinates are, how to convert from spherical coordinates to rectangular coordinates and vice versa, as well as discuss some good surfaces, some constant surfaces involving these spherical coordinates. In this video, we will be discussing how to integrate using the spherical coordinates as well as how to develop the theory in doing all of this. Now without further ado, let's begin. Now suppose that we have a function f that is continuous on my solid G. If you remember, in the derivation of the triple integral, if we assume that this function f is our density function, we can talk about the mass of G. And we'll do that by partitioning our solid G into smaller parts. In the rectangular case, we partitioned it into rectangular boxes. In the cylindrical, into wedges. In our case, in the spherical coordinates, we're going to divide it in what we call a spherical wedge. A spherical wedge is like a rectangular box. However, instead of being measured by a delta x, delta y, and delta z, it will be measured by the following. Firstly, this will be a change in the phi. This length here is a change in the rho, and this length here will be a change in the theta. Of course, the rho here will be a length, while the phi here and the theta are angles. Doesn't change the fact that if I want to find out the mass of this spherical wedge, I need to be able to get the volume, since mass is equal to density times volume. To do that, I will first let rho sub L star, theta sub L star, and phi sub L star to be the center of the spherical wedge. One important part of this proof is that it should be the center of the spherical wedge. Unlike in the rectangular case where we can just choose any random point inside our rectangular box, in here it should be exactly the center. That will mean that rho sub L here is the midpoint of the endpoints here, and so is the theta and our phi. Given this center, it can be shown that the volume of each of these wedges will have this following formula, and that is the volume is given by the rho sub L squared sine phi, and I have delta phi, delta rho, delta theta, and delta phi. Because of this fact, we can, if I add all of these spherical wedges that I used to cut my solid, then therefore the Riemann sum will be given by this formula, the summation of, this was the volume before, while f evaluated at this very complicated quantity will be my density. It may look complicated, but since my function should be evaluated at x, y, z, I just made x to be rho sine phi cosine theta, which is exactly rho sine phi cosine theta. And then y will be rho sine phi sine theta, z will be rho cosine phi. Evaluated, of course, all at rho sub L star, theta sub L star, and phi sub L star. Then, of course, as you have seen many times before, if I let n go to infinity, this will become much finer, giving us this very beautiful quantity, the triple integral of f evaluated on the converted xyz times rho squared sine phi d rho, d theta, and d phi. Something important to note here is that there are three main things that changed. First, instead of having a dv, you will have this quantity here, which is very much similar to what we learned in the polar coordinate system. If in polar we have the r, dr, d theta, we have a multiplier here which is rho squared sine phi. Very important part in the completion of the spherical coordinates, integration in spherical coordinates. The second change will be the x, y, and z. Since I want everything to be in terms of rho, phi, and theta, then I need to convert the x, y, z correspondingly, as was indicated in those formulas on the left side of the screen. And last but not the least, if before I have I have limits in terms of x, y, and z, then now the limits will be in terms of rho, theta, and phi. Of course, it should be in this order. Now, to aid us later on in our discussion, I will be again posting this formula on the left side of the screen for our benefit. Now, before I go to the solving proper, a very important note here, a very, very important observation will be that unlike the rectangular coordinate system, where we can interchange the variables x, y, and z, in spherical, we rarely do so. And that means that most of the time, we will go with the order d rho, d theta, d phi. Not saying that it is impossible, but being able to interchange them means it becomes more difficult than usual. So we will be limiting ourselves mostly on the case where this is always of the form d rho, d theta, d phi. I will also be discussing it in this manner. If in case you were able to find questions where you can do so, of course, that is also acceptable, but rarely done in this course. Being said so, let's have the following suggested steps in setting up the triple iterated integrals in spherical coordinates. As usual, drawing will be the first part. Of course, being able to draw means that we will be able to understand our solid properly. And then we will be finding out the limits of the rho, the theta, and the phi in that order. First will be the limits of the rho. To get the limits of the rho, I will draw a ray from the origin emanating, going outward. It will enter at the solid rho equal to rho sub 1 and leaves at rho equal to rho 2. You will see here how important it is that I was able to isolate rho, because the right-hand side does not have the rho as a variable. I am referring to one of the notes and helpful tips I have said in the previous video, where if you were not able to isolate the rho in your equation, you will have a difficult time. That's also true in finding rho sub 2, because this is only dependent on theta and phi. After getting the rho, we get the limits of theta. This may be the easiest because this is exactly the same limits in the cylindrical coordinates. That is, we just need to project the solid to the xy plane and find out the theta that is being considered in that projection. And last but not the least will be the phi. This will be the newest of them all. This is sweeping g. From the positive z-axis, the first angle it will consider will be my gamma, and the last will be my delta. I will be discussing this again and again in our next examples. So without further ado, let's have our first example. I wish to evaluate this triple integral where g is a solid within z equal to square root of x squared plus y squared and x squared plus y squared plus z squared equal to 2. Just like what we did in the rectangular and cylindrical coordinate system, we don't really need much to analyze z. It will come later on. The thing to analyze first will be the g. In this case, this is a solid within this curve and this surface. And if you notice, this surface is just a cone. A cone facing upward with vertex at the origin, which, as I have said before, a very good surface. This is a sphere centered at the origin of radius squared of 2, which is also a very good surface. If you draw this, it will look like this. So I will have a cone, vertex at the origin facing upward, and then you will have a sphere, and I will only need to consider the upper part of this hemisphere, upper hemisphere, because that is the one that will have connection with our cone. Now, since I now have my solid, the next thing to do is to note that the equations that we have right now are both in rectangular form. One good thing to do is to first express them in their spherical coordinate counterparts before we proceed. For example, the x squared plus y squared plus z squared equal to 2. Since it's just a sphere centered at the origin, we'll have the equation rho equal to the radius, in this case, square root of 2. While the cone z equal to square root of x squared plus y squared, as we have done in the previous exercises, we'll just have equation phi equal to pi over 4, given as follows. Because of this, we can now try to analyze the limits of integration. We start with rho. To get my rho, what I'll do first is I will make a line from the origin. It will emanate outward. The first quantity that it will touch, or the first values that it will touch, will be the first limit, and the last will be the where it exits. You will see here that since the vertex here is part of my surface, the first rho will be 0 because the origin is there. And it will exit at the time when the rho is equal to square root of 2. You will see wherever I draw a ray, it will always start at the origin and will end at the equation rho, or the surface rho equal to square root of 2. Now how about theta? For theta, since I just need to project my solid to the xy plane, which is giving me a full circle, that will mean that my theta will be from 0 to 2 pi. And last but not the least is for phi. For phi, I will start at the positive z-axis, and I will start rotating it like so. Since the positive z-axis is part of the positive z-axis part of the solid, if I will start rotating it until it exits it, and you will see it will exit it the moment it exceeds pi over 4. So therefore, the phi here will be from 0, which is from the positive z-axis, until pi over 4, giving me the limits of integration. And therefore, we have the following. I can now express this triple integral in its spherical coordinate counterpart. Remember, there are three main changes. First will be the dv. It will become a rho sine phi d rho d theta d phi, as is indicated on the left part of our screen. The next one will be the limits of rho, theta, and phi. For the rho, as I have discussed before, will be 0 to pi over 2. For theta, 0 to 2 pi. For phi, 0 to pi over 4. And for our last change, I will change my z in terms of rho, theta, and phi. In this case, that will just be a rho cosine phi. Simplifying it, I will have the following triple iterated integral. At this moment, we can forget all about the figure because we just need to solve this as a normal iterated integral. And that is, first, anti-differentiate it with respect to rho, evaluate, anti-differentiate with respect to theta, which in this case there is none, so that will just be a theta from 0 to 2 pi, giving me 2 pi, and integrating this with respect to phi, and thus giving me an answer of pi over 2. Now you will see here that when I expressed my integral in its spherical coordinate system, it becomes much easier. For one, if I try to solve this in rectangular coordinates, you can imagine the horror because, firstly, if this is a type xy solid, you will have a hemisphere which definitely will have a square root of 2 minus x squared minus y squared, minus this cone which also have a square root of x squared plus y squared. Not only that, in terms of the xy, since this is a circle, then that will give me limits of the form square root of 1 minus x squared minus square root of negative square root of 1 minus x squared, with x from negative 1 to 1. So it's one thing that it will become a hard integral. At the same time, it's very hard to evaluate because you will have a lot of square roots, which means you need to use trigonometric substitution and some other techniques and it's even possible that you won't be able to evaluate the integral. So if evaluating this integral in spherical coordinates really helps us in evaluating it. Another thing is that if you notice, when I express this in spherical coordinates, all of the limits are constant. And there is something that we can do when it is constant, and it's the following remark. A very interesting occurrence is what happens when you have two functions, fx and gy. If you notice, f is only dependent on x, g is only dependent on y. And you integrate the product of these two functions over limits which are all constant. What will happen is that instead of anti-differentiating it using iterated integration, what I will just do is I will integrate separately all the x's and all the y's. That is, if all the integrand variables can be grouped via multiplication and all the limits are constant, we can just integrate the variables separately. To demonstrate this, for example, what we learned is that our triple integral will be of this form. You will see all of my limits are constant, and we can separate this multiplicatively, all the rhos, all the phis, and we don't have thetas. What this means is that I can just isolate all the phis. So 0 to pi over 4 will be the limit of phi. We don't have a theta, so that will be from 0 to 2 pi, and all the rhos will be limited from 0 to square root of 2. We can anti-differentiate this all at once. Antiderivative of this is sine squared phi over 2. The other one will just be a 2 pi because that's just the length. And rho cubed will just be rho to the 4th over 4, evaluated from 0 to square root of 2. At 0, this is 0. At pi over 4, it's 1 half times 1 half times 1 half. That will be a 1/4 times, of course, 2 pi. And if I evaluate rho to the 4th at square root of 2, that will just be 4. So that will give me a 1, which is the same answer as we have before. So truly, using spherical coordinate systems will make our evaluations much easier. Of course, provided that all of the limits are constant. Let's have another example. So I want to find the mass of my solid G, given that the solid is above the xy plane, outside the sphere, x squared plus y squared plus z minus 1 squared equal to 1, and inside the sphere, x squared plus y squared plus z squared equal to 4. And its density function is given as follows. So what I need is the mass. And as you remember, mass will just be the triple integral of my density function. As I have said before, I will be first ignoring my density function and analyze what my G is. So if you look at the bounds that I have, the xy plane is a very good plane, as I have said in the previous step. Spheres. The sphere is centered at the origin, which is a very good surface in regards to the spherical coordinates. And if you can see this well, x squared plus y squared plus z minus 1 squared equal to 1 is a sphere tangent at the origin with tangent plane xy plane. So all of these are surfaces that has a good counterpart in spherical coordinates. And we will convert all of them. For 1, x squared plus y squared plus z minus 1 squared equal to 1. As we have shown in the previous video, is just rho equal to 2 cosine phi. X squared plus y squared plus z squared equal to 4. This is a sphere of radius 2, and thus rho equal to 2. And thus, if you draw it, it will be of this form. We need to only analyze the ones above the xy plane. So we are analyzing the upper hemisphere of x squared plus y squared plus z squared equal to 4. And I need it to be outside as well of this sphere, in this case of equation rho equal to 2 cosine phi. Now that we have a drawing, we can set up the triple iterated integral. We can, unlike the previous example where I stated the limits one by one, we can actually do it already in our integral if you can do so. So again, there are three main changes here. For the dv, it will be rho squared sine phi d rho d theta d phi. For the limits, we do it one at a time. First will be rho. Now for the rho, if I make a line from this point going outward, you will see that since it's this outside part is the one that we need to study, then it will start at this surface, which is rho equal to 2 cosine phi, going to rho equal to 2. Remember, the reason why we need to isolate rho is because the isolation will become the limits. In this case, that's 2 cosine phi to 2. For theta, clearly the projection of this solid to the xy plane will be the full circle. And that means that the theta here will just be from 0 to 2 pi. And last but not the least, for phi, if I make a line, I start from the positive z-axis going and try to go down in this way, you will see that I will end at the xy plane, which is exactly pi over 2. It's an angle. So therefore, I will have from 0 to pi over 2 as my answer. So that will be my second change. And my last change will be the one in blue. I, of course, need to change this in terms of rho, phi, and theta. And since this is exactly rho, I will have the following answer. Simplifying it, it will give me this. Now, unlike the previous example where we can split this, in this case, we cannot, simply because of the presence of 2 cosine phi. As I've said, you can only split when every other variable is, all of the limits are constant. Since we have a variable in one of our limits, then we cannot do that. And thus, I just do it the old-fashioned way. I will anti-differentiate and then evaluate. Anti-differentiate again and evaluate. Anti-differentiate, evaluate to get me the answer, 32 over 5 pi. Now let's have another example. How about finding volumes? So in this case, I want to find the volume of the solid in the first octant, inside the sphere, and under this cone. We'll do the same technique. Firstly, volume means that I want to evaluate the triple integral over my g of 1. So there's no integrand here to be a problem of later on, so that's just a 1. And then afterwards, I will be interpreting all of my surfaces as into their spherical coordinate counterpart. For example, x squared plus y squared plus z squared equal to 1 will just be rho equal to 1. The cone will be a little bit more complicated, but I know how to evaluate cones. And that means I will just use the fact that tangent phi will just be square root of x squared plus y squared over z. And since z is just the square root of 3x squared plus 3y squared, if I factor out square root of 3, cancel out the square root of x squared plus y squared, I will obtain 1 over square root of 3. There's only one phi that satisfies tangent phi equal to 1 over square root of 3, and that is precisely phi equal to pi over 6. Remember, I will only be doing this in the first octant, and thus I will have the following. So I have something inside the sphere, so this is our sphere, something inside it, the first octant, and I want it to be under the cone. Now this is clearly our cone, and it is wrong to say that I will study only the things under this small part of the cone. Remember, a cone extends indefinitely. So therefore, every part of this one will be also under some part of the cone. So I'll have the following diagram. So let us try to set up our triple integrals. As I have said before, this is divided into 3 main parts. The dv, again, will be rho squared sine phi d rho d theta d phi. Now for the rho, again, drawing a line from the origin outward, clearly origin is part of my solid, and it will exit at the surface rho equal to 1, so I'll have 0 to 1. For theta, the projection will just be the quarter circle, so it will be from 0 to pi over 2. And for phi, unlike in the previous examples where you have something in the positive z-axis, in this case we don't. It will start when you have phi equal to pi over 6, and it will continue until the xy plane. And since xy plane is just pi over 2, you'll have pi over 6 to pi over 2. Very similar to our first example, since all of our limits are constants and you can separate this multiplicatively, we can use the splitting method that I have taught you, but we will not be doing that here. I'll do the old-fashioned way of anti-differentiating, evaluating, anti-differentiate, evaluate, and then you anti-differentiate, evaluate again. You can check the computations here. They are very, very simple and very, very easy. Now let's have one last example. Now this is where the triple integrals in spherical coordinates shine. And this is true especially when you deal with triple integrals in rectangular coordinates that have a lot of square roots. For example, this problem here, if you try to solve this in rectangular coordinates, you will have a hard time because even just the first part means you will need to use trig subs here, and you will have square roots here, which if you try to evaluate, it will become a very, very big mess. But what I can do here is to change from one coordinate system to the other, is to generate my drawing based on the limits that we have here. Now, what we clearly, since the limits for z will be z equal to square root of 4 minus x squared minus y squared, we have seen that a lot. Squaring both sides, I'll obtain x squared plus y squared plus z squared equal to 4. That's a sphere of radius 2. Since I will start at z equal to 0, that's just a hemisphere of radius 2, centered at the origin. While the bounds for the x mean that the square root of 4 minus x squared equated to y will give me a y equal to y squared plus x squared equal to 4, which is just a circle of radius 2. Since I'm doing it from the negative to positive, that's the full circle since I considered the limits of x as negative 2 to 2. So that's just a circle of radius 2 centered at the origin. The drawing will be something like this. So I will be considering the whole hemisphere. So the bounds here talk about the whole hemisphere of radius 2 centered at the origin. Therefore, we can now express this in its spherical counterpart. Firstly, we have the following quantity. We will do this part by part. Firstly, the dz dy dx is just the dv. In this case, my dv is rho squared sine phi d rho d theta d phi. For the limits, I'm already done in looking at this quantity since I already have my solid. So I will analyze this. For the rho, from the origin outward, the origin is included. It will stop when you are in this part, which is in this hemisphere of radius 2. So that will be from 0 to 2. The projection to the xy plane is just the whole circle. So theta here will be 0 to 2 pi. And for the phi, from the positive z-axis going down, you will see it will cover from 0 to pi over 2. Last but not the least, I will express the whole integrand in terms of rho, phi, and theta. Z squared is just rho cosine phi squared, while the square root will just be rho. Simplifying this, I'll have the following, which we can again split if you want, but I won't, and I'll just integrate, and then evaluate. You will see how big the change from the rectangular system to the spherical. Though it is also wrong to say that I will express everything in terms of spherical so that it becomes easier. As a concluding right for all of the triple integrals, there is no such thing as the best coordinate. You will need to look at the solid and your integrand and decide on what coordinate system that you really need to use. For example, if you have a lot of cylinders, maybe cylindrical system will be the best for you. But if you have a lot of spheres and cones, possibly it's the spherical coordinates. Of course, no one will tell us that rectangular coordinate system will be the worst because there are some solids that can only be analyzed through the rectangular coordinate system. Now, I hope you learned well in this video. I hope you enjoyed it. Thank you for watching and stay safe.